Now, conversion of a galvanometer into a voltmeter. Now, we are provided with a pointer type tabletop galvanometer that is to be converted into a voltmeter. So, for the calibration, we are provided with a potentiometer arrangement also. Now, let us discuss the theory involved in the conversion of a galvanometer to a voltmeter and calibration of this voltmeter, converted galvanometer with the help of a potentiometer. Our aim involves three parameters. First one is we have to determine the galvanometer resistance and the current sensitivity of the galvanometer, that is current sensitivity K, where K is the current required to produce a unit deflection on the galvanometer. Now, we want to check the converted galvanometer, that is the new constructed voltmeter, with the help of a potentiometer, that is to calibrate, and then we have to draw the calibration curve. Now, let us discuss the theory involved. Now, if you are having a galvanometer, that galvanometer can be converted into a voltmeter by connecting a high resistance X in series with that. When such a connection is made with the galvanometer with a series resistance X, say where if G is the galvanometer resistance and X is the high resistance that is connected, and if K is the current sensitivity, that is the current required to produce a unit deflection, then we can write G plus X into K, that is equal to 0.1, such that the galvanometer is converted to read 0.1 volt per division. The galvanometer is converted to read as a voltmeter, where the voltmeter reads 0.1 volt per division. Then we can write the formula G plus X into K, that is equal to 0.1. Now, from that we can write X as 0.1 divided by K minus G. So, first we have to determine the value of X, and then we have to connect this X in series with the galvanometer. Then only this particular galvanometer is converted to an voltmeter. Now, for that we require the value of G and K for the calculation of X. So, the first part is we have to determine the value of the resistance of the galvanometer and the current sensitivity of the galvanometer, then only we can determine the value of X. Now, for that we are using a circuit arrangement like this, that is for the determination of G and K. Here, as you can see in the diagram, two resistance P and Q are connected. Usually the value of P and Q are such that P plus Q is 1000 ohm, or it can be 2000, that depends on the value of the galvanometer resistance. So, you can decide the value of P and Q. Usually P is 1 ohm, 2 ohm, 3 ohm, etc. So, that P plus Q is 1000. Then when a accumulator is connected, a current flows through the resistances P and Q. Now, we are connecting a galvanometer through a resistance R across P. Initially the value of R is 0, then the potential difference applied across the galvanometer is the potential difference across P. Now, we are using a commutator also. The purpose of the commutator is just to reverse the direction of current through the galvanometer. Now, when from the theory of the half deflection method, what happens that let initially with the value of R 0, let the galvanometer gives a deflection D. The galvanometer gives a deflection D because the galvanometer is connected across P. The potential difference across P is given to the galvanometer. So, the galvanometer gives a deflection D. Say let that deflection is D, or we can say an example, say 12. Then by the principle of the half deflection method, now we are introducing a value of R. Now, we can change R value, we can put any value of R. Now, unplug a certain resistance in R such that the deflection produced in the galvanometer becomes D by 2. Now, in our example, if you are getting 12, now the deflection should become 6. Find which value of R gives a deflection 6, and that value of R corresponds to the galvanometer resistance, that is the half deflection method. Now, we can repeat the experiment because now we can change the value of P. If we are taking P initially say 2 ohm, now change P to a value of 5 ohm. Then the potential difference across galvanometer increases, galvanometer shows a higher deflection, say let the galvanometer shows a deflection of 60 for example. Now again find the value of R to make that deflection half d by 2, that is 16 by 2, that is 8. Again we are getting almost the same value, and that is again the galvanometer resistance. So, we can repeat the experiment for different values of P, and each time we are finding the value of R to produce half deflection, and the mean value of that R is the mean resistance of the galvanometer. That is the method we are determining the resistance of the galvanometer. Also, we can find the value of P by D from this experiment. Each time we are changing the value of P and we are noting the value of D. So, P by D is calculated. Then we can determine the current density with the formula K is equal to E by P plus Q into 1 by G P by D. We mentioned E is we are connecting an accumulator there. So, E is the voltage of the accumulator, usually 2 volt. P plus Q we have taken either 1000 or 2000. G now we obtained, that is the galvanometer resistance. P by D, that also we determine in each time. P by D is also a constant. So, substituting these values, the current sensitivity K is determined. Now, we obtain G value and K value. From that we can determine the value of X. Now, X is equal to 0.1 divided by K minus G. Now, if we connect this X value in series with the galvanometer, now the galvanometer is converted to a voltmeter. Now, it is converted to a voltmeter. Now, we want to calibrate that. Now, for the calibration is done with the help of a potentiometer. Now, for that initially the potentiometer is standardized with the help of a Daniell cell. So, we are having a potentiometer between A and B, that is the primary circuit. The accumulator E, key K and rheostat is connected. Now, in the secondary circuit we included a Daniell cell. And then the balance length corresponds to the Daniell cell is determined. Then we can obtain, it is standardized, the potentiometer is standardized, we obtain the potential difference per unit length of the potentiometer wire is 1.08 divided by L. Potential difference per unit length of the potentiometer wire is 1.08 by L. Now, the converted galvanometer, that is the galvanometer together with the resistance X in series, that is a high resistance, is connected. The Daniell cell is removed from the secondary circuit, then the converter galvanometer is connected here. Then we can move the jockey over the potentiometer wire. Now, the jockey is moved over the potentiometer wire such that, say, the galvanometer gives a deflection of say 1 unit or 1. Now, when the galvanometer gives a deflection of 1, that means the voltage is 1 into 0.1, because we converted this one to a galvanometer which reads 0.1 volt per division. So, if you are getting a division number of division 1, then the voltage is 0.1. Then jockey contact is determined for which value of giving 1 division. Now, that L value is determined, that is L, small l. Then we can determine the potential difference across the voltmeter using the formula V is equal to 1.08 L by capital L, where capital L is the balance length for the Daniell cell and small l is the length that we obtain for a deflection of 1 division. Now, we are having two values of V. One is calculated value of V, 1.08 L by L, and the other one is V0. V0 is, that is the voltage noted from the voltmeter. If it reads 1 division, that is 0.1. Now, we can repeat the experiment. Now, for that jockey is moved such that the galvanometer reads say 2 division, then the voltage is 0.2. Say again moved so that the galvanometer reads 3 division, then the voltage is 0.3, and each time we note the value of L, that is the distance between the jockey and A. L is changing and the voltage is calculated. So, each time we are getting V0 value and the value of V. Then we are determining the value of V minus V0, and that is the correction in the voltmeter. Now, using the value of V and V minus V0, we are plotting a graph, that is the calibration graph, where V0 is plotted along the x axis and V minus V0 along the y axis. Now, coming to the tabular column that we used. Now, we mentioned we usually are taking P plus Q is equal to 1000 ohm. So, initially we want to find the value of G and K. So, we have the tabular column for P and a tabular column for Q. Now P plus Q is always 1000. So if you are taking P say 5 ohm, then Q should be equal to 995. Now if you are taking P as 10 ohm, then Q should be equal to 990. Then coming to the galvanometer diffraction. Now here we are having two columns, left and right, and then mean. That means when a certain value of P is introduced, now the galvanometer shows a diffraction. So we mentioned earlier we obtained a diffraction of say 12. Then when commutator is changed, the diffraction is in the opposite direction, that is the left and right. Then mean value of diffraction is noted. Then we can determine the value of P by D. Now P is here, P by D is calculated. Then next column, resistance for half diffraction, that is also left, right and mean is there. Left means when the galvanometer shows a diffraction say 12 centimeter to the 12 division in the left side. Now we are introducing the value of resistance from the box, so that the diffraction becomes half, and that is the value here R for resistance for half diffraction. Now when the galvanometer shows a diffraction the right side, then also we are taking unplugging the value of R, that is the value of R for half diffraction in the right side. So left and right, the mean value of these two gives the value of G. So we obtain P by D and G. Then the experiment is repeated for another value of P, say 10 and Q 990. We determine the value of P by D and G. The experiment is repeated for P value say 15, 20, 25, etc. Then we obtain mean value of P by D and G. Then K is determined, E by P plus Q into 1 by G, P by D. We obtain K. Now using the value of K and G, we determine the value of X. Now that X value is connected, then we are doing the calibration with the help of the potentiometer. Now in the galvanometer, the jockey is moved such that galvanometer diffraction is say 1, 2, 3, 4, 5, etc. diffraction the galvanometer. Then the voltage V0, when it is 1, the voltage is 1 into 0.1, because each division reads 0.1 volt, then 0.1 volt. When it is 2 division, it is 2 into 0.1, that is 0.2 volt. Now each case we obtain the value of L, that is the length of the wire from A to jockey, that is L, that is noted here. L is noted in each case. Then the value of V is calculated using the formula 1.08 L by capital L. So using the value of V and V0, we determine the value of correction, that is V minus V0. Now a graph is plotted and we obtain the following results. The galvanometer is converted, the calibration graph is plotted, the current sensitivity is noted. So that is the result of the experiment. Now coming to the experimental setup for the conversion of galvanometer to voltmeter. Actually we want to find the value of X, a high resistance that is to be connected in series with the given galvanometer. Now for the calculation of X, as we have seen in the theory, X is equal to 0.1 divided by K minus G, where G the galvanometer resistance and K the current sensitivity. So in order to calculate the value of X, we want to find out the value of G and K. Now to find out the value of G, that is the galvanometer resistance, and the value of K the current sensitivity, we are using a circuit diagram like this. This is the circuit diagram we used, we already explained. Now we have two resistance P and Q that is connected to an accumulator and a key. So here this is the resistance P. We can unplug any value of resistance here. A resistance box we are using, that is the resistance P. From P, as we have seen in the diagram, P is connected to the positive of the battery. So this is the positive of the accumulator. It is connected to P. It is connected to P. Now the other side of P, is connected to the resistance Q, that is also a resistance box. We can take any value of resistance in the resistance box. Usually we are taking P plus Q equal to 1000. So usually P is equal to 5, then Q is equal to 995. Now the Q is connected to a key. Now a key is connected to Q, and that is connected to the negative of the battery. So that circuit is complete. Now in the other part, now across P, we are connecting a resistance R. Now from P, from the point here, now this is the resistance R. The end of R is connected to a commutator. So here we are having a commutator. The other end of the commutator is connected to the other side of P. That connection is here. Now the opposite two terminals of the commutator, we included the galvanometer. Now this is the two opposite ends that is connected to the galvanometer. So, the galvanometer is included here. That is the connection diagram or the connections that involved in the determination of G and K. Now, to start with, initially we are unplugging a key, say 5 ohm. Now, here a resistance of 5 ohm is unplugged here from the resistance box, that is P is equal to 5 ohm, and the value of Q is you can see here 500, 200, again 200, 900, 50, 950, 990 and 995. So, a value of 995 is introduced in the resistance box, that is Q. Now, when the commutator is given contact, here, you can observe on the galvanometer. Now, we can observe on the galvanometer there is a deflection of 6 divisions. So, that is the value of D. For a value of P is equal to 5, the deflection in the galvanometer is 6 division. Now, we want to introduce the value of R. So, we have to take some resistance in R, so that this deflection becomes half, that is we want to make the deflection to a value of 3. So, we are taking different values, say initially we are just checking with a value of say 500. Now, what happens that the reading becomes almost 1, that is not possible. So, by trial we are taking another value, say 200. Now, again the deflection is not 3, the deflection is only 2. Now, I am taking another value, say 100 here, I am taking a value of 100. Now, the deflection is almost 3, not exactly 3, almost 3. So, I can take a small fraction of values, say 5 ohm, 2 ohm, etc. So, when I am taking 5 ohm, now I am getting exactly the deflection becomes 3 divisions. So, initially with the R 0 value I got a deflection 6, but with an R value 105 ohm I got the deflection becomes 3. So, we note the readings. The left side deflection is 6, we obtain a deflection 6 in the galvanometer. To make the deflection to a value of 3, the R value included is 105. So, that 6 and 105 are noted. Now, again the R is replaced, the R value is replaced, becomes 0. Now, the commutator is reversed, we are changing, we are rotating the commutator is reversed. Now, what happens that you can see the galvanometer shows a left deflection exactly almost 6. Now, the galvanometer shows a deflection of 6. We are not changing the value of P and Q, just the commutator is reversed. Now, the galvanometer shows a deflection of 6. So, we note that deflection in the left deflection, that is 6. Again, we are introducing some value in the R, again we are trying for that 100. Now, for 100 the deflection is coming to a value of 3, then say 105, 106, etc. So, that we are going to see for which value the deflection becomes 3. Now, for 106 I got the deflection becomes half the value, 3 divisions. So, we noted that reading also, the deflection is 6 and the value of R is 106. Now, we are repeating the experiment, again the R is made 0 again, the keys are included. Now, we are changing the value of P, the P value is changed to a value of say 10. Now, in P, in the box, in the resistance box, we introduce a resistance P here, that P is equal to 10. Now, when the commutator is given contact to one side, we are getting the one deflection. Now, the deflection is nearly 8 or 9. Now, the deflection is 8. So, earlier we obtained a deflection of 6 only. Now, when P value is increased, we got a little more deflection. Now, the deflection is 8. Now, we want to find the value of R again. To make that deflection is half the value. Again, we are trying for different values, say 100. It is not coming to a 4 value, it is nearly 5 now. Then again, we are adding some other values, say 110 I tried, then 112. Now, for 112, what happens that the deflection 8 becomes 4, that is half the deflection. So, we can note the readings, deflection to one side is 8 and the value of R is 112. Now, interchange, the direction of the current is changed, that means commutator is reversed. Initially, R value becomes 0 again. commutator is reversed. Commutator is reversed. Now the deflection is 8 in the left side, the other side. Again we are taking the value of r, trying for different values, say 110, 111. Now for 111 we can mark the value 111, the deflection becomes half the deflections. So we are repeating for another value of say P is equal to 12 ohm. Again we are getting the deflections and R value. Now P is equal to 15, 17, 20 etc. It is repeated, and the mean value of G, and also each time we can calculate the value of P by D. The P by D value and the G value are determined. Now with the help of that P by D, here I am getting a P by D value of say 1.0886 and a mean G value of 100.83. So using that value of P and P by D and G, we can calculate the value of K. Now K is equal to E by P plus Q into 1 by G into P by D. We substituted E is equal to 2, P plus Q is equal to 1000, 1 by G, G is equal to 100, P by D is equal to 1.0886. So I got the K value here. Now we obtain a K value 2.159 into 10 to the power of minus 6. So G is 100.83, K is 2.159 into 10 to the power of minus 6. So X is calculated. So we are calculating X value. So 0.1 divided by 2.159 into 10 to the power of minus 6 minus G. So we obtain the X value as 4533. So the high resistance that is to be connected in series with the galvanometer is 4533 ohm. So we determine the value of X. Now we want to connect that X value and calibrate with the help of the potentiometer. Now coming to the last part, that is the calibration. Now the galvanometer is already converted. We are going to connect a resistance of 4533 ohm in series. Then that unit become a voltmeter. Now before calibrating that, we are using a potentiometer. First we want to standardize the potentiometer. Now for that, now the potentiometer arrangement is here. Between the two terminals A and B, the accumulator is connected to A. Then a rheostat is included. The rheostat is connected to a key here, and that from that key it is connected to B. That is the connection between A and B of the potentiometer. So through the potentiometer wire a certain current is flowing. Now we can adjust the rheostat in the primary circuit, that is the rheostat here. Now in the secondary circuit we are having a voltage source. That voltage source is providing exactly 1.08 volt, that is the voltage of the Daniel cell. So we are in the initial stage, that is for the standardization of the potentiometer, we are using a Daniel cell having a voltage of 1.08. Then we are giving the jockey is giving contact on the potentiometer wire through the galvanometer, through a galvanometer. So when we are giving contact somewhere to near to A, so in the first row we can see we are getting a deflection in the left side. When we are giving a contact on the end B, we are getting a deflection on the right side. So we have to find out where we are getting a zero deflection. So we are trying for that, where we are getting a deflection, zero deflection. So we have to find out the point for zero deflection. Now somewhere here we are getting zero deflection. Now that is corresponds to on the sixth row. Now this value is corresponds to 640. 640 I am getting here. For a 640 the deflection is 0. On the other rows we can see there is a left deflection, on the other row the deflection in the right, and exactly at 640 at this particular point the deflection in the galvanometer is 0. So that is the balancing length capital L for the Daniel cell. Now for the second part, for the standardization, for the calibration of the galvanometer, the Daniel cell is removed. The Daniel cell is removed. The Daniel cell is removed from the circuit. Now the resistance box is included, and we are including, we already mentioned, the resistance to be connected in series with the galvanometer is 4553. So we are using a resistance box, and from that resistance box a resistance of 4000, now 2000, 2000, 4000, 4500, now 4543 for 2020 and 3. So 4543 is included. So that resistance is connected in series with the galvanometer. Now we can give contact. The galvanometer jockey can be given contact to some point. So we are observing to get some deflection. Now we can observe. Now the galvanometer is given contact. We are getting deflections. So we are getting deflections. Now move the jockey to a particular point such that the galvanometer gives a deflection of say 1. It is difficult to take. So we are trying to take a deflection of say 3 divisions. Now here when we moved, now you can see here. Now I am getting here somewhere here. What happens there? Find an exact value. Now the galvanometer deflection is 3 division. So we are converted this galvanometer to read 0.1 volt per division. So there are 3 division is there. Now the converted voltmeter reading or V0 is 3 into 0.1, that is equal to 0.3 volt. Now I got the balancing length L. Now L is equal to 180. So we are marking that L value in the tabular column. So L we obtain 180. Now using that L value we can determine the value of V. Now V is calculated as 1.08 into L, that is 180, divided by capital L, that is balance length of the Daniell cell, that is 640. So I calculate the value of V here. Now here V is equal to 0.3036 I obtain. So 0.3 is the voltmeter reading and the calculated reading is 0.3036. So we can calculate the correction, that is 0.3036 minus 0.3, that is equal to 0.0036 volt. So that is a correction. Now we are repeating. Now we are moving the jockey to some other point. So that the deflection in the galvanometer is say 4 division. So 4 division. So we are trying for a deflection of 4 division. We are moving the jockey. Now what happens that at this particular point, the reading on the galvanometer is 4 division. So the voltmeter reading is equal to 4 into 0.1, that is equal to 0.4 volt. But the balance length is 240. So I can calculate the calculated value of voltage V, that is equal to 1.08 into 240, that is L, divided by capital L, that is 640. It is calculated. Now we are calculating that value. So that is 1.08 into L divided by 240, L is 240 divided by 640. I am getting a value of 0.3771. So the voltmeter reading is 0.4, but the calculated value is only 0.3771. So V minus V0 is negative here, that is 0.3771 minus 0.4, that is minus of 0.0289. Again we are repeating. We want to get a reading of 5 division on the galvanometer. Now we are trying for 5 division where we are getting. Now we are trying for that. Now here what happens that the galvanometer gives a deflection of 5 division. Now it is in the third row going to 300. Now the balance length is 280. So for 5 division, that means the voltmeter reading is 0.5 volt. The balance length is 280. So we can calculate the V0 value is 0.5. Now the value calculated value of V is 1.08 into 280 divided by 640, that is 0.4725. So again we are getting a minus value, that is 0.4725 minus 0.5, that is minus 0.0275. Now we are repeating. We are moving the jockey to different points such that the galvanometer gives reading or divisions, say 8 division, 10 division, 12 division, 14 division, 20 divisions, etc. In each case the balancing length L is determined and the value of the voltage measured from the voltmeter, that is V0, and the calculated value of V is voltage is V, and V minus V0 is calculated. Now coming to a sample set of readings for the conversion of galvanometer to voltmeter, we mentioned we have taken P plus 2000. The accumulator voltage is 2 volt. Now we want to determine G and then K. For this is the tabular column. Initially we use P as 5, then Q 995. Now we obtained a left diffraction 6 in the galvanometer. Now in order to make this 6 half, we introduce R3 for half deflection, and that is 105. Now commutator is reversed, then we are getting a deflection the right side, that is 5 only. To make it half, that is 2.5, we introduce a resistance say 105. So the mean of these two deflection is 5.5. Then P by D is calculated, that is 5 divided by 5.5, that is 0.909, and then mean of these two resistance, that is 105, and that is now the last column we can note that here we are adding a correction also. The correction is like that. Usually if you are taking P value say 1, 2, 3, 4, 1, 2, 3, 4 etc., that is more correct, then directly we are getting the value of G. But if you are using some higher values of P, then there is a correction is there. The corrected value of G is R3, or that R value minus P only. So in each case we are subtracting the value of P also, then we are getting the value of G. Now the experiment is repeated for 10. These are the readings that we obtained. For 12, 15, 17 and 20 we repeated, and in each time we obtain the value of R3, and R3 minus P is calculated, and that is taken as G. And mean P by D we obtain 1.0886, and mean G is equal to 100.83, and K is equal to E by P plus Q into 1 by G. P by D is calculated, that we obtain 2.159 into 10 to the power of minus 6 ampere per scale division. Now X is calculated using the formula 0.1 by K minus G, 0.1 by 2.159 into 10 to the power of minus 6 minus G. G is equal to 100.83. So we obtain a very high value of resistance, that is a high resistance, that X is equal to 45330 ohm. Now this high resistance is connected series with the voltmeter, and then it is converted to a voltmeter. The galvanometer is converted. Then using the potentiometer for the calibration, initially we obtain the balance length for the Daniell cell is capital L is 640. Then we move the jockey when the converted galvanometer is connected in the secondary circuit. Now we obtain for a deflection of 3 divisions. Initially we obtain 3 divisions. Then the voltmeter reading is actually 3 into 0.1, that is 3 volt only. Then we obtain a balance length of 180 in that case. So in order to give, or in order to get 0.3 volt or 3 division in the galvanometer, we obtain a balance length of 180. Then the calculated value of potential difference is 1.08 into L, 180 divided by 640, that is 0.3036. Then V minus V0 is calculated here, that is 0.0036, 0.0036. Then it is repeated, jockey is moved, so that the galvanometer reads 4 division. At that time the V0 value is 0.4 volt. We obtained a balance length 220. Then V is calculated as 0.3711 only. Then the correction is, now here the correction becomes minus, that is minus of 0.0289, that is V minus V0. Similarly, when we repeated, or when the jockey is moved, for divisions 5, 6, 7, 8, 9 up to 14 we repeated. Now for 14 we obtain 14 into 0.1 volt, that is 1.4. At that time we obtain a balance length of 940. Then the calculated voltage is 1.5862. Then the difference is 1.5862 minus 1.4, that is 0.188. So each time V minus V0 is calculated, and we are supposed to draw a calibration graph, and that is the result of our experiment.